Oleg, you can start your talk.
Oh, may I start? Yeah, good.
Sure.
First of all, I said in Ukrainian, дорогі наші одесити, дорогі наші київляни, люди, які захищають нашу землю від кацапської навали, я вам дуже вдячний. І ми всі з Львова висловлюємо вам найкращі бажання і мужності вам, щоб ми перемогли і добили ту всю заразу. Я бажаю в першу чергу вам здоров'я, особливо одеситам. Ви самі знаєте, що відбувається в Одесі, що я говорю. Я також вдячний всім учасникам конференції, які підтримали своїми доповідями, своїми думками нас в цій важкій війні. So thank you for all organizers for a very nice conference, and thank you very much for all participants of the conference and for the support of our conference. And my report will be very, very classic in the topological algebra. What will be? So I shall start with some definitions. Yeah, just a moment. So if we have x, y, and z are topological space, then when we consider the map f from the product x, y to z, this map is called right continuous if it is continuous on the right variable, yeah, if for every fixed point x0 from x, the map from y to z, which is defined by this formula, is continuous. And left continuous is defined by the dual way. So separately continuous if both if this map is both left and right continuous, and jointly continuous if it is continuous as a map between the product space x multiply y and space z. So in the next definition there are some problems. Why? I use the definition, classical definition from the set-theoretic topology, but some topological algebraists use it dual definition. So if S let S be a non-void topological space provided with a substitutive multiplication, especially in semigroup operation, yeah, mu from S squared to S, we define such formula. Then the par S mu is called a right topological semigroup if the map mu is right continuous equal S of interior left shifts lambda S is defined by the formula x maps to x sx are continuous maps, and dually we get a left topological semigroup. Some specialists in topological algebra write topological semigroups called left topological semigroups. Because they think that left shift are continuous map. And semi-topological semigroup if the map mu is separately continuous. And a topological semigroup if the map mu is jointly continuous. The next. And similarly, we shall say the topology in semigroup S is called semigroup topology if the pair S tau is topological semigroup, shift continuous topology if the pair S tau is a semi-topological semigroup, and left continuous topology if this pair is a left topological semigroup, and dually a right. So it's correct, a right continuous topology if this pair is a right topological semigroup. So the problem of topologization of any algebraic structure is very, very old. In 1930s, Markov and other mathematicians posted the following equation, very, very simple. If we have algebra does there exist a topology in this algebra such that which is not discrete? And or in other way, does there exist an algebra such that any Hausdorff topology is discrete? So, and this problem is called the problem of non-discrete topologization. So the next problem, which is similar to this problem, the problem of embedding inside some compact or compact algebras. For example, when some algebraic semigroup embed into compact topological semigroup or in compact semi-topological semigroup, and so on. So this is my previous course told that this problem is called Markov problem in topological algebra, because Markov poses this problem officially in 1945. So what is motivation was? So Potagin in his book Topological Groups gave well-known 5 conditions on the system of neighborhoods of unity of a group for its non-discrete topologization. And first group or manifold or variety of groups was constructed by Alexander Olshansky in 1980. He constructed an infinite count of groups such that every T0 topology, so with respect to it, this group operation and inversion are continuous, is discrete. But before the solving of this problem by Olshansky, there were 2 very nice examples. First example, it was the example of Eberhard and Seller of bicyclic semigroup, but very nice example was constructed by Adapt Taimanov. He constructed a commutative semigroup T, which admits only discrete Hausdorff semigroup topology. Also, after that, Taimanov gave a sufficient condition on a commutative semigroup to have a non-discrete semigroup topology. But in the general case, there are no condition, there are no sufficient condition that the topology for topology on a non-commutative case. And this Taimanov semigroup is a very nice semigroup because more than 10 years ago, I proved that any T1 topology on such semigroup, such that the shift in this semigroup are continuous, is discrete. This semigroup is have many good conditions. For example, the first condition that any T1 semi-topological semigroup contains Taimanov semigroup as a closed sub-semigroup. And hence we get that Taimanov semigroup does not embed into compact semi-topological semigroup, into countably compact semi-topological semigroup, and other semigroup is properties that with such properties that like a compact condition preserved by closed subsets. And I should start with very nice semigroup, the bicycle semigroup, and to result about bicycle semigroup, about topologization that's a result of Karl Eberhard and John Selden, that the bicycle semigroup admits only the discrete shift continuous Hausdorff topology. So this result was extended by Bertman and West for semi-topological semigroups because Berkha Alexander proved this result only for Hausdorff topological semigroups. So the bicycle semigroup also has many bad properties. For example, compact topological semigroup does not contain countably compact with squared topological semigroup does not contain pseudo compact. It does not contain the bicycle semigroup as a dense subsemigroup, and so on. There are many results which are presented in these three papers. The main result of my report will be two sub-semigroup of the bicycle semigroup with the following property, that any Hausdorff left continuous topology is discrete, or any right continuous topology is discrete. We consider two sub-semigroup of the bicycle monoid C plus PQ, so which is defined by this formula, and C minus. And it is below that C plus and C minus are anti-isomorphic submonoid of the bicycle semigroup is trivial result, and every Hausdorff left continuous topology in the monoid C plus PQ is discrete. And dually, we get that every Hausdorff right continuous topology on the monoid C minus PQ is discrete as well. But C plus PQ and C minus PQ admits a non-discrete locally compact semigroup T1 topology, and C plus PQ and C minus PQ admit a shift continuous compact T1 topology. Also, we have a very nice description object closure of the C plus and C minus semigroup. Yeah, if the monoid C plus PQ is dense subsemigroup of a Hausdorff semitopological monoid S, and I, which is equal S without C plus PQ is not empty set, then I is the closest to second ideal of the semigroup S. Also, we construct a compact Hausdorff topological monoid which contains the monoid C plus PQ, and similar we get for C minus PQ. But I remarked that the bicyclic semigroup does not embed into compact Hausdorff topological semigroup. And we construct the following two examples. The semigroup C plus PQ, it must be here, PQ, admits a non-discrete right continuous topology TP minus, which is not left continuous. And the semigroup C minus PQ admits a non-discrete left continuous topology TP, which is not right continuous. So what does it mean? That we get that any left continuous topology on the monoid C plus AB is discrete, but this semigroup admits a non-discrete right continuous topology. And below this topology is not left continuous. So this two example is not simple. We use it the technique of periodic topology on the additive group of integer and extend this topology on such two semigroups C plus PQ and C minus PQ. And that is all my result. Thank you for your attention. Бажаю всім мирного дня, спокійної ночі і радості. Thank you.